Thank you very much for showing up so early in the morning. And I could understand that many of you had doubts about this presentation. The rumor has it that Chris and I only met 48 hours ago, and actually that's true. And both of us don't really have English-speaking names, so thank you very much for your courage in showing up this morning. The title of our presentation is Hiding in Plain Sight, and we want to discuss advances in malware covert communication channels. My name is Pierre-Marc. I work with Dell SecureWorks. In my work, I do mostly malware analysis and security research. And I'm here with Chris, who likes very much fancy animals and graphical design. Try to guess who he works with. But I think Chris can introduce himself a bit better than that.
Hi, everybody. My name is Chris Dietrich. I work for a company called CrowdStrike, and I'm mainly doing reverse engineering and analysis of targeted attacks. But today, we want to talk about covert communication channels, and especially about malware command and control. Now, being security researchers, and especially malware researchers like Pierre-Marc and myself, discovering a new malware family happens every now and then. That's not necessarily something new. But a couple months back, we were both working on a case which stands out among what you usually see out there in the wild. And that is because we've seen a malware which uses Steganography in order to hide parts of its command and control communication. And at that point, we decided to join forces and to work together on this case and drive research on this, most of which ended up in what we're going to present in this talk. Apart from that, we try to broaden up the objective of this talk a little bit, so we will also cover a few more examples of malware families, malware samples that are out there, real-world malware samples that are out there in the wild using hidden communication methods for malware command and control.
This. Excuse me, I'll just try the pointer once more. All right. So here's the outline of this presentation. As Chris mentioned, we first started working on malware that was using Steganography to hide communication channels between an infected device and its command and control server. And during our discussions and investigation, we started to realize this was actually a trend. We were seeing more and more malware trying to hide the communication that they had with their command and control server. So in this presentation, we will cover mostly two topics of Steganography and inconspicuous carrier protocols. I also want to emphasize that we really want to document cases that have been seen in the wild, that we have observed for real. So we're not going to make hypotheses or try to invent new communication channels that might exist, because there are many more. We really want to focus on real cases that we have seen. Before going into a lot more details, let's first step back and look at why would malware want to communicate? And why does malware need to communicate with a command and control server? Well, first of all, a malware needs orders, or it needs command to perform its tasks. Pretty much the only task we could think of that would not need any kind of communication with a command and control server is if you are creating a destructive malware. In this case, the malware probably doesn't need to communicate with anybody. It just knows when it reached its target, and it will destroy it. But in other cases, if you want, for example, to make network reconnaissance, then you need to interact with the malware. More precisely, you need the malware to receive command from its operators, to send feedback on that command, how the command was executed, did it succeed or not, what kind of result it brought. You might want to send updates for the code if you want to fix bugs or introduce new features. And finally, you might be interested in exfiltrated data, you being the malware operator, of course. In order for communication from an infected device to the command and control server to be efficient, it needs to happen, meaning that it shouldn't be blocked by any kind of security mechanism. Either human beings investigating a case, like forensics analysis or incident handlers, or automatic tools like intrusion detection systems or antivirus. To ensure that we are all talking about the same thing here, I prepared one quick slide of definitions. I promise that you don't need to go back to your bed right now. This will only be one slide. So to us, covert channels is the capability to transfer information between two hosts, which are not explicitly allowed to do so. In a corporate environment, if a system is infected, well, it's probably not allowed explicitly to communicate with its command control server. There has been other usage, well, there are other usage of the covert term in cryptography, for example, but this is not the case. Here in the context of our presentation, this is how we want to use this term. Steganography is the practice of concealing messages inside non-secret text, data, or media. And what we call a carrier protocol is the underlying protocol which is legitimate that can be used for command and control protocol. So when you think about malware communication, I'm guessing that many of you here have had to deal with malware cases either from an incident handling perspective or for reverse engineering purposes. Usually when you think about malware communicating with its C2, it will be using something maybe, yeah, the usual will be HTTP traffic, maybe using encryption, maybe not. So this would be your average bot, your average Zeus or ASProx, cut whale. This is what we think is not necessarily very sophisticated. And I want to be very clear here. When I'm talking about sophistication, I'm really only talking about the communication channel, not the malware at large or overall, but really the communication channel. We've seen cases that were a bit more sophisticated, that were a bit more evolved. We've seen APT28, for example, using emails to send command back, probably adapting their communication method to a specific environment where they really wanted to have communication between an infected node and the command and control server. We've seen Stuxnet using removable drives. But in both cases, if a human looked at the files, they were probably able to figure out something weird was going on. What we want to discuss in this talk is something a bit more stealthy. Is malware using steganography and covert channels to hide their communication so that even humans looking at the situation will have a very hard time figuring out what's going on. And once again, I am not saying that the cases we've analyzed here are more complex or sophisticated than Stuxnet. Not at all. I'm just saying that the way they communicate might be. Now we have all these fancy terms and definitions, but really, to be honest, steganography is just a cool excuse to look at kittens. So, Chris, do we have any malicious content hidden in here? What do you think?
So you want me to do applied steganography detection in that?
We are senior researchers. This is what we're tasked with.
Usually I do that reverse engineering, but I don't know, maybe after a few beers I start seeing strange messages in that picture, but right now I just see a cute little kitten.
And you're right, this is just a cute kitten. There is no steganography in there. Just wanted to share the happy morning. But how about this one?
I don't know if you look at the same picture, but that's just a bunch of servers, right? I mean, a photo of a rack of servers.
Yeah. Well, this one is a bit tricky. Actually, I wanted to have an example of something that we don't necessarily consider to be steganography, but actually is used by malware. So this image was taken from one of the Zeus KINs command and control server. And there is something in the image. Let's have a deeper look. When you look at the header, this is the hex dump of the header for this file. So you see it's a JPEG with the header JFIF over there. But the rest of the fields seem to be okay. There is no HTML tags, for example, that some of you might have seen yesterday with the conference on Stegosploit. It seems okay. But when you scroll down and look at the bottom of the file, there is a base64 encoded string appended to the image. So when an image reader accesses this file, it can render the file, the image, no problem. You can see it, and it's an image of a server. But at the bottom, you have a configuration file. It's encoded with base64 and then decrypted with RC6. This doesn't fit our definition of steganography because if a human looks at the file, they will see that there is something appended at the end. They need to look at it in an X editor, of course. And automated tools will not have a very hard time detecting this because clearly something is odd at the end. The entropy, for example, will not be the same at the end of the file. And once you decode this config, this is what the configuration looks like. So you have a lot of information stored into this base64 string once it's decrypted. You have the version of the bot, you have the different command control URLs, what kind of information it should be stealing. So this is just to show you that some malware are appending data to images, but this is not exactly what we consider to be steganography. Moving on to our first example of malware we've seen using steganography. This example is with Gauzy NeverQuest. So Gauzy NeverQuest has different names. So Vautrak is another alias of this malware. It appeared a long time ago in 2007. The main objective for this malware is banking fraud. So they're going after banking credentials and they're trying to make fraudulent transfer of money between different accounts. They do so by stealing credentials, but then also installing VNC plugins, for example, and SOX proxies on infected hosts so that they can control the accounts and transfer money. Another interesting characteristic of the malware is that it very often deletes the browser history whenever it manages to infect a computer to remove anything that might lead to the infection vector for the malware. The real communication, or the main communication channel used by Gauzy, is what I would call standard, or it doesn't fit the sophistication layer of steganography. The standard way a Gauzy infected host will communicate with its command and control server is using HTTP posts, and it's going to use LCG cryptography with APlib compression. So far this is not really a good candidate for our presentation. But earlier this year, Gauzy started to use a Covert channel. And they added the capability for steganography in the beginning of 2015. The way the malware does it is by downloading a file called 5icon.ico, and these are the little images that you see on pretty much every web server these days that are giving you a small icon to represent the website when you're saving it as a browser bookmark, for example. Gauzy will download this 5icon over SSL from a Tor node using the Tor2 web service. It will then extract the least significant bit from each pixel in that file, decrypt it using RC4, and retrieve backup servers. So the Covert channel is only used as a backup mechanism when the infected host cannot communicate with its command and control server anymore. It will try to use this Covert channel to gain connection back to its command and control server. So for those of you who are not very familiar with the least significant bit steganography, here is a quick diagram of how this works. If you want to hide information inside an image, you can basically change some of the information that is encoded with every color. So when you're parsing a file, you look at every pixel. And in the case of least significant bit steganography, you can alter the last bit and flip it to fit with the message you want to transmit. And in this case, the changes are so small that they are very hard to see by the human eye. So we see here that we have a first orange pixel, and you can start encoding 4 bits in it, 1101, etc., etc. What's interesting to note here is that actually you will be encoding, you have some limits in the size of the data you can encode inside this image compared to the size of the image itself. So coming back to Gauzy, Gauzy uses least significant bit steganography to download a 5icon.ico file. It then strips out the header, doesn't care about the header, then extracts a configuration file, which is signed. So we have the white mark at the top of the middle box here. And from there, it extracts a list of backup command and control server, actually just the domain names for these servers that they will contact when they lose contact with the main server. And this is what we see in this XDump of the decrypted configuration file for Gauzy NeverQuest. Moving to the second example of malware using steganography. This malware is called Lurk. So let's see if we've learned anything about this steganography thing. How about this one? And no, the slide is not broken.
Oh, yet another test?
Oh, yes.
Yet another steganography?
Yeah. I want to make sure you don't fall asleep.
It's a white slide. I mean, there can't be anything in there.
Oddly enough, there is. Lurk is hiding some data in BMPs that are usually look like this. They're completely white. So Lurk is a malware family that was first discovered last year and documented last year. It's a downloader. So it's used to install click fraud malware. So by itself, Lurk only downloads and installs more malicious stuff on infected hosts. But to retrieve the URL of the malware it wants to download, it will actually download a BMP image and extract the least significant bit information from each pixel and to retrieve the URL after some basic XOR encoding for the payload. It's interesting to note here that the malware author didn't even take the time to use nice graphics or even cats maybe, but they just kept the white images. Lurk also uses steganography for hiding code of its modules that come bundled with the main binary. So there are a couple images inside the resources of the PE file that contain code. But this code is also encoded inside images. But in this case, it is very visible by the human eye. So it's not exactly fitting our definition of steganography, but still, this is another example of malware in the wild that has been seen last year, actually using steganography to hide communication. Moving into the case that we quickly mentioned during the introduction, Stegoloader. You like bears, don't you?
That's a fancy bear.
That's a fancy bear. So is there, do you think that there's anything hidden in this image?
I would be tempted to say no, but you know, I learned. So this time I say maybe.
Maybe. Actually, you're right. You know your animals, so that's very good. In this image, this is one of the examples of images that are used by Stegoloader to hide content. This is actually a PNG image. Stegoloader is an information stealer. We first started seeing incidents involving this malware at the beginning of this year. The component of the malware that uses steganography is the downloader module. So this is the first executable that will start executing on a machine. And this downloader module is used to spot analysis environment, only execute if the malware thinks that it is running on a real machine and not inside any kind of analysis environment. It then downloads an image from a legitimate website, and this is something new. Extract the main module code from the image. So compared to Lurk and Gozi, which were extracting only URLs from the images, in this case, Stegoloader extracts code, x86 code from the image, and then directly launch the main module code from memory. So the images don't touch disk, and the code for the main module never touches the disk either. What the malware does once it's running, once the main module is running, is that it will create a pretty verbose profile of the infected host. It will try to list its characteristics, and we will see a bit more details on that later. Depending on the characteristics of the infected host, the malware operator will push different modules that will be executed afterward. The infection vector for Stegoloader is a bit odd. The infection vector that we've seen are actually, the files are downloaded from websites pretending to be delivering key generators or crack software that are used to bypass, to crack software basically. And some of these websites are actually delivering new variants of the malware every day. And once you start the executable that you downloaded from this crack site, you have a UI for a real key generator with a nice 16-bit music. So if you've analyzed it, you will remember that. But also it drops a copy of Stegoloader that starts executing. Some of you might also be interested by the detail that these websites also always have a CAPTCHA. So whenever you want to download a file, you need to solve one of the CAPTCHA. So either this is to slow down automatic crawlers trying to fetch the files, I'm not sure. Coming back to our bear image and the steganography. Stegoloader actually extracts least significant bit information from PNG images. So we have our picture here at the bottom of this diagram. We have the LSB extraction. Then the malware, the code is going to be decrypted using RC4. There is some validation done also with a CRC32 at the beginning of the encrypted block of data. And then we end up with code that is going to be executed directly from memory. So I know you like animals, but I also like nice sceneries. So what do you think about this one?
There's no cat in there, there's no bear in there, but I still say yes, there's something in there.
You're learning, you're good. This is another example of images used by Stegoloader. I actually downloaded hundreds of them, and they're all different, but they're all nice to look at. So I'm sharing this with you. Stegoloader has a lot of interesting characteristics. It has many tricks to find, to identify analysis environments, both automated and the tools that might be used by researchers. The first one it uses is to resolve what I call funky imports. So in different or in specific analysis environments, for example, antivirus emulators or sandboxes, some features are added. So there might be, for example, functions that will be resolved inside standard DLLs that will resolve in an analysis environment, but that will not resolve on a real system. So on the example I have here, and I know it's a bit small, but I trust that you can read it on the slides you can download from the website. The malware tries to resolve the import mp start process from kernel32.dll. This is not a function that is exported by kernel32.dll on a standard system, but in some environment it is. So the malware, if it achieves to resolve this import by calling getProcAddress, it directly exits. So it won't show any other behavior, it won't do anything else, it won't decrypt itself to execute, so it will just stop executing. So this is the first trick used to identify analysis environment. Stegoloader also closely monitors where the pointer of the mouse is on the screen, trying to ensure that a user is really playing with the system when it's executing. This is done by calling the getCursorPause function. But the malware doesn't call it once or twice. It actually calls it in an infinite loop until the mouse moves. But if the mouse moves too fast, meaning that if it jumps in different position, they also stop execution and will never execute again. So the guys that did this malware really want to make sure that it only executes on their target and not necessarily when some researcher or some sandbox is running this malware. Strings in the binaries are constructed dynamically, so the characters are pushed on are moved on the stack before using the strings, so that if you're running strings, for example, on the binary, you pretty much won't find anything. And finally, the malware also lists the processes that are running on the machine when the malware is executing. So if there is a network traffic capture program running, or if there is something like procmon, any kind of debugger, WinDBG, ODDBG, the malware will stop executing directly without exhibiting any kind of malicious behavior. Interestingly enough, the malware also has a lot of debugging messages or debugging facilities embedded inside it. Using a different command and control server than its main command and control server, Stegoloader sends status messages or debug messages to a server that is different using strings like this one shown in this example. And it will actually report every stage of its execution once it's passed the check for analysis machines. So it will say, yep, I was able to allocate a page of memory. Okay, I will download an image. Oh yeah, the size is okay. Yeah, it is consistent. I'm able to load the GDI plus library that will be used to actually process the PNG afterward.
Does it also report if it's a beautiful image or not? Or?
It doesn't have a lot of taste right now, but yeah, it's a good question. No, not yet. But I find it really odd that I just told you about all these checks and how stealthy the malware is, and then when it starts running, it spits out pretty much everything exactly what it is doing. And we had a couple theories about this.
Yeah, we thought about this. Why is that the case? Why does it make sense for a very complicated malware to have this kind of reporting channel? And so, I mean, of course, if you design or if you write very complex software, you have to have debug output or debug reporting at some point. So that makes sense. But why do you leave it in there for, for long-running campaigns? And I think we have like two hypotheses, right?
Yeah. So our first hypothesis was that maybe this is an affiliate program. Maybe the guy, maybe the people operating this malware want to get paid whenever the malware is running, so they want to know exactly where it's running, how it's doing, so that they can collect the money somehow. But yeah, we were still not sure about this. The other one would be that the operator is a different entity than the programmer. And in this case, the programmer is allowed to receive debug information, but they are not allowed to access the command and control infrastructure used by the operator where stolen data can reside or where more specific data can reside. So this is a bit more of a complete explanation how Stegoloader works. So we were telling you about the deployment module that downloads the image and starts the main module. Once the main module executes, It will create a profile of the infected host, send it to the server, and then try to download new modules as they are decided by the command control server. The different modules that we have observed so far are there is one module used for geolocation, so trying to identify where the host is located based on its IP. There's a module that is used to list recently opened documents by looking at the folder recently opened documents in Windows and following all the links. There's a password stealer module, which is a recompiled version of the pony loader. And finally, an IDA stealing module. So if the malware finds that there is IDA installed on the host, they will send specific code to grab all the IDA folder, the IDA key, the executables, the installer, the plugins, any code you might have in there, and they will send it out to SandSpace. I'm pretty sure there are other modules dependent on other characteristics of an infected host, but these are the ones that we've seen. What's really odd is that we've also seen some other payloads being delivered as binaries, as PEs that would be executed on the machine. For example, we've seen some Vundu samples or PunMockup, which are more like click fraud malware. And we don't know if this is part of the monetization for this malware or if it is just a distraction so that people wouldn't really pay attention too much to the malware itself. So the monetization in this case is still a bit of a puzzle to us. What's also interesting is just like Gozi, Stegoloader actually communicates with its main command and control server in a way that we do not consider to be very stealthy or very sophisticated. I mean, it took a while to analyze, but it's still relatively standard. HTTP posts with RC4 encryption, and then you have different messages that are being sent. Many of them are in JSON format. Some of the data in there is encoded with base 64. If the message is bigger than 0x200 bytes, it will be compressed with LZMA. So this is more of a standard communication protocol that we would see.
One of the interesting aspects to mention there maybe, one of the interesting aspects is that the RC4 keys are actually, they vary over time. And they are hard-coded in the binary, so they are not derived from the messages or from some environmental properties. But they're just changed regularly and hard-coded in the distributed binaries or in the distributed code via the images.
Very good point, thanks. We've also realized that actually the way that different modules are being pushed to infected hosts kind of is organized in scenarios. So you will usually have a first interaction with the command and control server where you will have, for example, send sysinfo. So the server will ask the infected host to send a list of system information. So you will have the name of the processor, the name of the graphical adapter, system, the version of the operating system. Then you might have another request to send a list of infected software, And then, depending on these first information, you will have another scenario or another set of interaction where we will have the different modules being pushed one after the other. And at the end, in all the cases we've seen, the infected host receives the kill command. And at that point, there is no persistence, there is nothing left on the system, the malware simply stops executing, and it's gone, and that's it. All right, so now we had nice animals, we had nice sceneries with winter, mountains. How about this one?
I'm giving up. Ask the audience. What do they think?
Do you think that there is any Stegoloader data or code being hidden in this image?
Who says yes? Is there yes?
I think the majority is right. Yes, there is. So this is another example of the images being used by Stegoloader, and in fact, I don't know exactly where they are taking all these images. So just to wrap up the steganography part of this presentation, as a summary, we've seen 3 recent cases of malware using steganography in real life. They all use least significant bit steganography, which is interesting. On the other hand, the 3 of them use different file formats, so ICO, BMP, and PNG. They all use some kind of encoding. 2 of them use RC4, and 1 is using custom encoding. What's very important to note is that steganography by itself is not a very good way of exchanging information between an infected host and a command and control server. There needs to be other technology to use, and this is what malware operators are doing right now, and that is compression and encryption.
Yeah, one thing to add there maybe is that all of those use lossless compressions in the image formats, and that's a pretty important point if you use or if you try to rely on steganography. Yeah, because if the compression is lossy, then you might end up decoding the wrong payload or the wrong data from what you originally intended to have encoded in that image.
Absolutely. Moving on to covert communication channels.
Thanks, Pierre-Marc. Okay, so up to this point, we have only looked at steganography as hidden command and control communication. But now we want to take a look at a few other examples of how you can hide malware command and control communication. So I have an example up here, basically two examples. Those are two DNS responses. The one in the upper half of the slide, and given in black, that's a typical DNS response as you would expect. Basically, what it does, DNS basically maps domains to IP addresses, and that's what we see in there as well. Someone was asking, what's the IPv4 address of the domain newcommunitybank.com? And in the answer section, you see this maps to an IP address 74.54.82.153, and it also has a time to live associated with it. In this case, that time to live is 1 day. In the lower part, however, this looks a bit suspicious. This does not look like a typical DNS request. But then again, DNS is flexible. You can do all kinds of stuff with DNS. But if we take this response apart, there's a few things that stick out. First of all, the query domain name is quite long, and it ends in google.com. Well, there's a lot of Google services out there, and who knows? This could be machine-to-machine communication, so could be. But the next thing that sticks out is the resource record type of that query is set to any. And that basically means give me any resource record that you have for that given domain name. And in the answer section, we see that the server actually responds with a TXT record. That's here. And in that resource record, we have a set of, or a text string, basically. And what's also interesting is that the time to live for that DNS response is 0, which basically means that response is not supposed to be cached in any kind of DNS resolvers. So at that point, this looks suspicious. And I can tell you that much. This lower part, DNS response, was caused by a botnet which uses DNS as a carrier protocol for its command and control. But before going into that example in depth, let's step back for a moment and think about why would it make sense to use DNS as a carrier protocol for command and control. Well, first of all, there's no specific detection for the DNS protocol. Now, don't get me wrong, I know there are several DNS-based protection means out there, but what they basically do is they apply blacklisting or whitelisting. And that means they target on the domain names that are resolved via DNS and possibly also on the IP addresses that are returned. But they rarely target the DNS traffic in general. So for example, if you're talking syntactically valid DNS with third-party resolvers on the internet, that's often allowed. For example, Google Public DNS or OpenDNS, there are several of these. And that's sometimes even allowed in, let's say, heavily firewalled environments. So in environments that try to restrict communication, but they do allow DNS to go through, and they do even allow DNS to go through to third-party resolvers. And from the perspective of a malware operator, DNS has a few advantages, and one of those being that it is designed as a distributed system. And that provides an advantage to the malware operator because distributed systems are typically much harder to take down than a centralized one. All right, let's look back at the example that I just presented. Basically, that initial request I showed you is from a bot that's called FeederBot, which we discovered in 2010, actually. So it has been around for more than 5 years. We called it FeederBot back then based on a characteristic string in the binary. And it has this fancy command and control channel, but regarding monetization, it basically just does ad or click fraud. It implements a covered channel via DNS, and that by itself is not really something new. That has been presented in the past many times. But if you're actually faced with a question or with a task of implementing such a covered channel, you're basically facing several decisions that you have to make. And it's interesting to see how exactly the malware authors faced these or solved these and designed the whole malware. For example, they have several query domain schemes. One of those is that they're using legitimate domains, like well-known domains like that google.com example that I presented earlier. And that requires that they either have control over the zone information for those domains, which is unlikely in the example of Google, or, and that's what they did in the example, they direct these requests to their own set of DNS servers. And that makes it a challenge for forensics because if you just see the DNS requests or responses without the information where this request went to or who answered that request, it's hard to tell if it's legit or if it's malicious. They are making use of a distributed infrastructure, but they are not using the inherent features of DNS, which is also interesting. Now I'll get to that in a second. But I can tell you that much. Their infrastructure is spread over multiple autonomous systems, so they are pretty aware that a distributed infrastructure is harder to take down. Now let's take a bit of a closer look at how this responses or this request and the response are made up or built up. So in the bootstrapping phase, that's the early requests that the malware sends out. It basically asks for more C2 servers or second stage C2 servers. And it does that, and it includes in the request a system-dependent bot ID, which is this 50-byte or 50-character string that you see up there. And that is used to encrypt the response by the server. If we take a look at the decrypted response that's given as a hex dump here, down here, then we basically see that there is an IP address as an ASCII string in there, and that IP address is used as the next stage C2 server that the malware then contacts in order to get more information about its tasking. So to sum up, it contains a referral to the next C2 server node, which is at the IP address that's on the slide. Now, there's a few more elements in that response, and it's interesting to see how it actually builds up the second stage C2 request. Now, on the top, we have that same referral in decrypted form as I showed on the previous slide, and at the bottom, right here, we have the subsequent or the second stage C2 request, so to say. And I'll walk you through how it builds up this second stage C2 request. There's 3 D words in that decrypted referral response and 2 ASCII strings. And the interesting stuff is that the first D word, the one marked in with a blue background, that is used as a subdomain of the domain that is supposed to be used to query the next stage C2 server. So basically, we have this magic number, the 26766. We have a domain name that should be used to talk to the second stage C2 server. In this case, this images movie.dyear.net. And we have an IP address, which is the IP address of the DNS server that is to be talked to. And we can also see that it specifically requests TXT resource records at this stage. Now, if you think about DNS, referrals are an inherent feature of DNS. If you think about iterative DNS resolution, you ask the root DNS servers and you get a referral back and so on and so forth. So they could have relied on that. But we suppose that, we think they did not, because you can't encrypt the information. You can't encrypt the referral if you're using the DNS inherent features. But you can if you do it that way. DNS has a few implications. So you can't make arbitrarily large DNS requests. It's based on UDP, so you have some size limitations, and the DNS RFC also has a few restrictions on the query domain name and stuff like that. But that's well respected by the malware. So the authors were apparently aware of that and worked around that. The basic message structure is that you have a DNS-TXT record. In that DNS-TXT record, you have base64 encoded data, and you have a CRC32, a checksum, 4 bytes basically, in order to check the decrypted content. And the actual content is what I refer to as a chunk. Because basically what happens is all the information that is to be transmitted is split up into chunks, and these chunks are transferred separately. And the chunk ID, or to query a specific chunk from the C2 server, that chunk ID is prepended to the query domain name upfront. So it's a pretty well-designed architecture or C2 protocol based on DNS. This malware again uses a variety of RC4 keys to make it, not a straightforward task to decode or decrypt the information. But as I said, it has been around since 2010, so apparently designing a C2 protocol in that way apparently helps to stick around for some time. Okay, that was an example, that was another cybercrime, typical e-crime, cybercrime example. But how about targeted attacks? Do we see DNS-based C2 channels in targeted attacks? Yes, we do. There's a malware family called PlugX, which has been around for some time as well. I think early variants go back to as far as 2008. And we see PlugX being used a lot. It has been used for many years. We have seen it being used against government entities, defense and aerospace sector, and even pro-democracy activists. It's mostly used by China-based actors, and it has a very modular plugin-based design. And as such, it supports multiple C2 carrier protocols, and among that is also a module to actually perform DNS-based command and control.
So are you saying that there is actually a Panda operating this?
There's a Panda using DNS for command and control. That's what I'm saying. Okay, let's take a look at an example. Compared to Feederbot, we see that this is structured a little bit differently. We again have a pretty long query domain name, and that's actually where the information is encoded in this example. So again, as I said earlier, there's a few implications that DNS implies, and that is, for example, that the domain name consists of labels. That's basically the stuff that's separated by the dots. And each label can only have a length up to 63 characters. And again, the malware knows that and works around it by inserting a dot at least every 63 characters. And the encoding scheme that's used here is basically base 16 using a custom alphabet. And it adds randomness in the first few bytes. So the question is, why does it do that? Well, adding random stuff to the query domain name helps to prevent this being cached. So because it's effectively a new query domain name, and caching resolvers won't add that to cache. Well, they might add it to a cache, but it's always a new one, so that prevents caching. But the interesting thing is that the byte at offset 3 in the plain text, which is offset 6 in the encoded variant that you see up there, that one is fixed because that's the message type. So it's always hex 1E in the plain text, and it's OB in the query domain name. So at that offset, you will always find OB for the initial bootstrap traffic in that case.
Are you aware of any public documentation on this feature of PlugX?
I don't think this says.
So these guys are hearing it for the first time?
I think so, yeah. I think it's first time publicly documented. Okay, leaving DNS aside for a moment, let's take a look at HTTP. Here's a typical HTTP response, I would say. So Pierre-Marc, you have been asking me so much about your beautiful animal pictures. What do you think? Do you see anything suspicious in there?
Well, to be honest, to me HTML is complete gibberish all the time. You have special characters and bigger, smaller, and no, I think this is completely legit. I mean, who doing HTML would do anything malicious? No.
It's not even a programming language, right?
Oh.
So, right, I mean, it's supposed to mimic a typical HTTP file not found error message. And that consists of a header, which has the status code, which is 404, and it also has a body. And that's typical for error messages as well. It just repeats basically that the file was not found, and the body is basically presented to the user. But what we see down here is actually there's some, encoded string. We can't say what exactly. It has a prefix of debug, so maybe they wanted to make this look like some state machine or state information. We don't know. But actually, if you decode that, you find that this is actually a command to a bot. So that's basically part of command and control communication, just hidden in a somewhat unique way. And this command basically tells the bot to download a specific binary from a specific location, execute it, and so on and so forth. Okay, that's it with our examples. Let's try to sum up what we've seen, or what we've presented in our talk. Now, these are real-world examples of malware that's using hidden communication. And we've seen examples from the cybercriminal world and from targeted attack activities. Covert channels are used by malware C2, and they are mostly used under certain conditions. And this is where it gets interesting. So we know that they combine that with cryptography. And they do that because just hiding the information, doesn't solve all your problems. If you combine that with cryptography, you actually make it difficult to signature the traffic, even traffic that is hidden. And they often do that for small messages. So coming back to the GOSI example, this is a really nice example. So why would you design your main command and control channel using steganography or any of those pretty complex techniques? And they solved it by basically just designing the fallback C2 communication using those techniques. If you think about the necessity to communicate, there might be some protocols that actually serve better if you need more bandwidth in the regular C2 communication. So far, we've only seen images, for example, for the steganographic part, and we've mostly seen DNS in these examples, and also HTTP. But, in order to scale up, you could also use any kind of other protocols, video conferencing, whatever protocols that by themselves use more or require more bandwidth. Part of that is that we believe steganography, at least, is mainly used for unidirectional communication. And the reason is, if you think about a two-way communication using steganography, let's say using images as the media you want to encode your stuff in, then you have to have a pool of images at hand that you can encode these messages in. And that might be doable for the C2 server side, but it's definitely more challenging for an infected machine to have that pool of images at hand to encode the messages in. If you use steganography, such as Stegoloader, then you can actually leverage benign infrastructure for command and control or malware storage. And that poses another problem for defenders, because that basically works around reputation-based detection or protection means. So finally, we've seen covert channels that involve steganography or hiding messages in carrier protocols make C2 communication more difficult to detect. But I would say steganography is not a panacea, and hiding messages in inconspicuous carrier protocols is neither a panacea. One of the main goals that we wanted to achieve with this talk is to raise awareness for this type of communication. And I think that's one of the first steps that we can take in order to detect this kind of communication in the future and If you ever happen to run across traffic that looks suspicious to you, just hit us up, get in touch with us, and we'll be happy to look into that. With that, I think we'll conclude this talk, and we'll take questions. Thank you for your attention. We actually have a little gimmick. So for everybody who gets up and asks a question, a real question, they'll get a T-shirt. So, think about it.
We might have a real question over there. Yes, sir.
So can you use RPZ or something clever on a DNS space to apply that?
Sorry, I didn't get it. Did you understand?
I think I understood the question, but I don't have the answer. Do you think a mechanism like RPZ can be used for this, for detecting or at least helping with blocking of this type of protocol? One, we're definitely not getting any T-shirts. I'll get back to you. I'm interested in knowing about this as well, and this is one of the topics about DNS that, I'm not sure. Are you?
No, let's chat about it offline, I guess. You'll get a T-shirt anyway. So, Mark.
Have you looked at or have you seen C2 mechanisms where they give specific commands or answers only based on the source IP or maybe the country or the net block of the particular victim, so that you can't really monitor it unless you're the victim itself?
A very good question. So the question was if we have seen specific answers based on the environment of the client or the infected machine. So, for example, based on the IP address. And the answer is definitely yes. So for Stegoloader, for example, as Pierre-Marc mentioned, they build up a very verbose profile of the infected machine. And we believe there's some kind of state machine implemented on the C2 server. And we don't always trigger the distribution or the deployment of the same payload. And we believe that is based on such things, such as the IP address that you're connecting from, maybe even how many times you have connected in the past. We've seen that pretty aggressive blacklisting, for example, by the C2 operators and stuff like that. So that is definitely a challenge for researchers. Yes.
I think there was a question in the back there.
So if I understood the question correctly, is how did they implement DNS covered channels? Okay, I got it now. The question is, how do they redirect the messages to their C2 service, to their DNS service, basically? Well, in most examples, they just send them directly to IP addresses that belong to their own infrastructure. They could as well use their own domains, and following the principles of iterative DNS resolution, they will at some point end up at the authoritative name servers, or one of the recursive resolvers will end up at the authoritative resolver that's responsible for that domain. So in that case, so if you use registered domains, you don't need to, influence that communication. But if you use use benign domains, basically, in that case, they directed them to those DNS servers that they set up or had under control.
There was another question over there.
Good point. So I think the question was if we had seen actors actively operating around blocking mechanisms that have been implemented as a result of detecting this type of traffic. I'm not aware.
Me neither. No.
Yeah. I think so. In short, I think they rely purely on not being detected, or we have not observed any other cases.
One question there.
Yeah, you concluded with saying that you observe only unidirectional so far communication, but in theory, wouldn't it be possible to dynamically encode the images so that the answer could essentially become bidirectional?
It would definitely be possible to encode information inside images and send it to a server, especially now that we're seeing more and more people trading images, sending images to one another. This is not even going to raise a lot of suspicion on a network. On the other hand, as Chris mentioned, it kind of assumes that the malware has a pool of images that they can use to encode messages in and then send over. And this is a bit less convenient for malwares to actually download images, do something. Or if they always trade the same image, then it might be a bit easier to spot. But I think this is more the limitation that we think is happening right now, why people are only downloading images and not necessarily trading them by hiding messages in both directions.
Two questions. First, have you seen different media formats like video or audio? And what clean sites did the malware guys use to hide images? You mentioned clear sites that can be used to override reputation systems. For
Clear.
example, upload image to image URL.
Okay, I see. So the question was which benign sites, which benign image hosting websites have been used in order to distribute the images that contained the malicious stuff? Okay. We've seen a variety of benign websites that were used to host that stuff, and that did change over time. So I think we have seen a total of like 5 or 6 hosting websites. I actually don't remember off the top of my head, but they weren't those big ones like Flickr or so. So there were smaller ones or medium-sized ones, I would say. None of them I had heard before, to be honest.
One of the most relevant I've seen is host-then-post.org. So this one has been used a lot. And actually the malware operators, maybe as a closing remark because we're out of time, the malware operators sometimes also were pretty quick to remove the images once they were used. So that was also interesting to note. But yeah, host-then-post.org was one of them. So thank you very much. If you have more questions, we will be glad to take them maybe offline. So because we're out of time. Thank you.
Thanks.